Thank you for coming to our talk on networking and communication optimizations for Llama 3. My name is Pavan Balaji. I'm a research scientist at Meta. I'm giving this talk together with Gangidi, who is also at Meta. Generative AI at Meta is fairly new. We started a few years ago. We started with Llama. That was our first model on the generative AI series. We moved on next to Llama 2. And most recently this year, we released the Llama 3 model in three configurations. The first was a 8 billion parameter small model, followed by a 70 billion parameter medium-sized model, and finally, most recently, a 405 billion parameter large configuration. Llama 3 is an open source model that is available for you to download all the weights. You can use it for your systems, and it is highly competitive with most proprietary closed source models, generative AI models out there. It is the largest dense model out there that is used in production today across the industry. Llama 3 itself is a back-end mathematical model. Of course, as a user, for you to interact with Llama 3, you need to use a product, one of the products provided by Meta to do that. That's where Meta AI comes in. Meta AI is one of our products that integrates with our family of apps, Instagram, WhatsApp, Facebook Messenger, and so on. You can see a picture of Zuck presenting this in the corner over there. And this shows, this is how you interact with our Llama series of models through this Meta AI product. Now, generative AI, as I mentioned, we've been doing it for a few years now, and it has gone through continuous improvement over these years. The first part, you can see on the leftmost image, this was in the Llama 1 timeframe in 2022. There's a prompt at the top that the user can add in as a question. For that prompt, you can see the leftmost image, it generates a picture. It's a good picture, but it's somewhat cartoonish in the way it looks. Okay, so that's still fine. If you fast forward 6 to 9 months, when we get to a Llama 2 sort of generation, we'll see that the picture with the same prompt at the top, we see the picture is much more realistic, much more richer with colors and so on. And of course, fast forward to last month with Llama 3, the picture is even more realistic, even more colorful, and so on. Now, the quality of the model, how good your responses are from the model, of course, is one part of the equation. But another part of the equation is how fast you can get responses from this model. You can train a very large model, so you get very high accuracy responses from it. But that comes at a cost of how fast you can train it or how fast you can serve it. Because if you have a very large model, it takes a long time to train or serve it. The trick is to get both of these together. You want a very large model to get high accuracy, but you also want to have very fast responses. So accuracy and speed are two strong duals that we need to manage together at the same time. That's where infrastructure comes in. That's where we need to build large, giant GPU clusters. We need to build a large network fabric to support this. We have to build fast storage systems, fast software, and so on and so forth. Now, as I mentioned, Meta has been in the generative AI, has been working on generative AI for a couple of years now. But AI itself, Meta has been working for a while now. We started with ranking and recommendation models, and we have been doing this for a few years now. And we, of course, built large clusters for ranking and recommendation models. There's a talk that happened last year at this Networking at Scale event, which you can take a look at, that talks more about our ranking and recommendation model clusters. Fast forward to Llama 2, we continue to use these models, use these training clusters for training Llama 2 models. By the time we get to Llama 3, we noticed that these clusters that were built for ranking and recommendation were not quite perfect for generative AI. They're good, but we can improve them further specifically for generative AI. So we started building clusters that are uniquely capable for fast generative AI training and serving. So we built 2 clusters, each with 24,000 GPUs, specifically for building out our Llama series of models, Llama 3 in particular. Okay, let's take a step back over here. We'll go through this talk in 4 different parts. We'll talk about the Llama 3 training itself and talk about what performance tuning we did throughout the process to get the best performance out of these clusters, specifically for Llama 3. We'll talk about the performance tuning part. Then we'll talk about the serving, the inference part of the models. So together with training, the other part we need to focus on is serving or inference. We'll talk a little bit about that. And finally, we'll close by talking about what the future holds for Meta with respect to our next generation of generative AI models in terms of our infrastructure as well as our network capabilities. As I mentioned, we've been doing ranking and recommendation for a while, and we moved recently to generative AI a few years ago. Ranking and recommendations, they have their own unique set of challenges compared to generative AI. For example, ranking and recommendation models run to a few hundred GPUs. They scale up to a few hundred GPUs. They have a full mesh sort of communication pattern. They exchange embedding operations, embedding data, sparse data, across all of the GPUs that they are connected with, which makes it a very all-to-all like communication pattern, full mesh like communication pattern. This makes it very hard to scale these ranking and recommendation models to two large clusters. Generative AI models such as Llama 3, on the other hand, they can scale much larger to tens of thousands of GPUs because they're more structured in the form that they do communication. They are either fully sharded or have parts of data replication through a distributed data parallelism model. And we have either a hierarchical or a Cartesian sort of communication patterns that allows us to scale our systems to much larger scales than what we can do for ranking and recommendation. We don't have a full mesh all-to-all sort of connectivity in these models, which makes it a little more interesting from a scaling perspective. Adi will talk a little more about that. Okay, with that, let me hand it off to Adi to tell us about the network topology and performance optimizations that we did for our training clusters.
Thanks, Pavan. So I'm Adi Gangidi. I'm a production network engineer at Meta, and I focus on our performance optimization initiatives, both focus on ranking models as well as our generative AI models. So before we dig into performance optimizations we did, let's spend a few minutes talking about all the workload artifacts that for generative AI models that Pavan talked about, how they influenced our network design for our 24K Rocky cluster that we talked about in the past events, right? So the building block of this 24K Rocky cluster is an AI zone. The AI zone in this configuration can support up to 3,000 GPUs with full bisection bandwidth. Now, we talked about generative AI workloads in the last slide scaling to tens of thousands of GPUs. So in order to form a big enough cluster to support these workloads, what we need to do is stamp 8 of these AI zones and connect them together with an additional layer of switching called aggregate training switches, or ATSWs. At this layer, however, we don't have full bisection bandwidth. We have 1:7 oversubscription. Now, how did we manage this? If you go back to what we just talked about, generative AI workloads have hierarchical collectives which produce traffic patterns like trees or rings. And for these patterns, they can tolerate oversubscription just fine. So in spite of all of this care that went into designing our clusters for these models, how did they perform out of the box? They actually performed fairly poorly out of the box, and the performance was variable as well. And we looked into why this is the case. Why are these large clusters not performing as well as our small clusters or ranking clusters that we've enjoyed roofline performance for years? And we came up with a series of understanding so as to why we were seeing such performance. Armed with this understanding, we tuned the collective library as well as the network config in order to make it perform better. Now, why was the performance not optimal to begin with, right? So there's 3 reasons. The first reason is that as Llama 3 workloads or generative AI workloads scale to a much larger size of tens of thousands of GPUs, the GPUs that were communicating with each other in a single communication operation also increased. However, they increased at a faster rate than the collective size or the message size exchanges between those GPUs. That means that we were becoming more and more network latency dominant. And apart from that, the system software or the communication library and other parts of software were not also tuned or optimized in the past to optimize for this specific aspect of network latency sensitivity. So the second reason why we saw poor performance was load balancing and hash collisions. In the past events, we've talked about hierarchical patterns not producing enough flow entropy. And for this reason, it's really, really hard to use hashing-based schemes in order to load balance such traffic patterns. And for this reason, we talked about us aggressively investing in traffic engineering initiatives. We initially started with these clusters with traffic engineering, but however, we quickly realized that traffic engineering, as we tried to scale it to more than the first network hop for load balancing to 2 or 3 network hops, we ran into operational problems in terms of the software complexity increasing, putting all of this to various vendors of switches in multiple tiers, as well as just the complexity of the controller software itself exploding. For this reason, we deferred to a load balancing scheme of enhanced ECMP or ECMP with flow multiplexing in all the 3 layers of networking to load balance. And that showed us, that resulted in much better performance. So flow multiplexing here refers to a series of changes that we do to the collective communications library to take each flow that would have been posted as in a single path as multiple flows or multiple queue pairs. This way, all of these parts of the flow earlier that would have taken on the same path now can take multiple different paths, and hence we can get much better load balancing, basically. So the third part is that out of the box, we saw much higher traffic on the third layer of switching that connected the AI zones than our modeling or simulation predicted. And the reason for this was our scheduler lacked network hierarchy awareness and hence was doing a poor job in terms of scheduling the jobs on these GPUs, resulting in too much cross-AI zone communication. Now, Veve and Arnab touched upon how we solve these problems by teaching the network hierarchy to the ML scheduler, right? So because of the limited time, we'll just dig into one aspect, the first aspect, which is the network latency sensitivity, and how we kind of understood more about the system software layer or collective communications layer, and then use that understanding to make performance better. So before we dig into what we did to improve performance, let's talk about 2 aspects of the collective communication library architecture that overall made it more sensitive to network latency. So there are 2 features that were very integral part of communications library used for training Llama 3 at Meta. They are two-sided communication and 2-stage copy. So let's talk about two-sided communication. What that means here is basically that if sender wants to post some data onto the network, it cannot do so right away until and of course it actually has some information from the receiver in terms of what is the size of the data that it needs to post, what is the memory location that it needs to post from, and what part of that collective that specific data belongs to. And this information is provided and posted by the receiver in a small message called clear to send to the sender. So now imagine this clear to send message actually got delayed because buffering, network buffering or congestion in the opposite direction. That means that the cadence at which we post messages actually slows down. So it's very, very important to get those messages back to the sender on time. Now, once we have this data, we can post this data, hopefully from our source compute buffer to the destination compute buffer, or from our sender to receiver, right? But because of the 2-stage copy architecture that we use in the collective communications library, these transfers from one buffer to the other is actually buffered by an interim buffer. Let's call that channel buffer before they get posted onto the network. Now, in terms of, as we post data from this channel buffer, you can only post data as large as the accumulation of channel buffers that you've configured. Now, you may say that if you want to post more data, why can't you increase the channel buffers to a very large amount, right? If you increase the size of these buffers, then you're taking memory away from other compute operations, model training, and other processes and things like that, which will actually eventually slow you down. So you cannot do that, right? So this kind of gives you an understanding that even when the workload and the collective sizes are capable of posting larger messages and saturating the network more and making it thereby less sensitive to network latency, we aren't able to do so because of the communications library architecture, right? So the final step of this handshake is basically now that the receiver has gotten the data, it needs to actually acknowledge or send some indications so that the sender can perceive a completion signal and get ready for the next data transfer operation, right? So, and this essentially process keeps going on and on and on. So yeah, so again, getting acknowledgement packets back from receiver to sender, also important if you want to, if you want the training process to continue again and again, right? So now, in this slide, we look at all the things that we did with all of this understanding about the collective communications library architecture in order to tune the network as well as the communications library to make it less network latency sensitive, right? So the first thing we did was, take the critical control messages like ACK and CTS and put them in a higher priority queue so that they don't get network buffering. They don't get subject to network buffering. How did we do that? We did this with network switch ACLs, as well as some collective communications library changes to mark these packets in a specific format so that the ACLs can actually pick up these packets and put them in a different priority queue, right? So the second thing we did, now we talked about control messages, the data messages that are on flight, they do get subject in our network to spine switches. Our spine switches use multi-chip architecture as well as a virtual output queuing architecture. And that essentially increases the handshake delay and the credit exchange between egress ports and the ingress ports adds some amount of latency there. So what we did that, instead of taking a generic algorithms for that credit exchange, we tuned that credit exchange algorithms from both in terms of the initial credit allocation from egress to ingress, as well as the credit ramp, specifically tune that credit exchange so that it's optimal for hierarchical collectives that are latency sensitive and things like that. So that actually reduced the in-switch residency time for an average data packet in flight. That also made us less network latency sensitive. The last part is, although we cannot increase the size of channel buffers by too large a margin, we can tweak it ever so slightly to put a little bit more outstanding data on the network, to saturate the network ever so slightly more, so that you're less latency sensitive. So all of these changes, along with other changes that we talked about related to load balancing and scheduling, helped us actually improve all-gather collective performance across message sizes above 10 percentage points. Now, that may not seem like a lot. When you're training as large a model as Llama 3, and which takes months to train, that could mean shaving off weeks in terms of training time. So it's very impactful work in order to actually understand the system software and the network, and to co-design both to get the best out of the network. So now that we talked about quite a lot about Llama 3 training and performance optimizations, back to Pavan to touch upon the model serving artifacts and the performance optimizations we did there.
Thank you, Adi. Okay, so let's switch gears a little bit. Let's move on to serving or inference. And as I mentioned earlier, it's important to have both model quality, accuracy, as well as speed, and achieving both is a challenge. So how does serving work? When you have, as a user, when you go and you go to one of the Meta products, go and enter your query. And it spits out a response for you based on your query. Now, that's what, as a user, you would be seeing. But in the back end, there are a bunch of things that are happening. The first thing that is happening is what is called time to first token. So after you enter your query, how long does it take for you to get the first word as a response, for the first output response? That time is called time to first token, and it's usually measured in an order of a few seconds. That's very network bandwidth intensive and very compute intensive and so on. That's the first part. The second part is what is called time to incremental token. So this is the time that takes after you got the first word response, how much time does it take to get the second word and then to the third word and so on. That's the time to incremental token. That's usually memory bandwidth intensive, but much more network latency sensitive, not network bandwidth sensitive. These are both important, and they both play a big role in the user perception of how good the product is. So as I mentioned, there are two parts to this, the time to first token and time to incremental token. The first part is bound by something called as a prefill, which is more network bandwidth intensive. The second part is bound by something called decode, which is more network latency sensitive. They're both obviously very important, but I'm going to focus more on the decode part, the network latency sensitive part. The prefill part is closer to what we look at for our training models, which Adi just talked about. So let me focus more on the latency sensitivity or the decode part of the serving. Now, to serve a model, of course, these are large models, so we need to have multiple GPUs on the back end to serve even a few requests. So these are broken down into two tiers, a prefill tier and a decode tier. Each tier has a bunch of GPUs associated with that. Within each tier, of course, there's data movement, there's communication that is happening, there's communication happening between these tiers as well, and you don't need to have a one-to-one mapping between the prefill tier and the decode tier. This is one form of inference system. It's called disaggregated inference. There are other forms existing as well for doing similar inference. Now, the most tricky part that we are going to talk about is within the decode systems, the communication latency that is needed. Now, one of the important aspects we need to do to get the decode latency, the time to incremental token, to be low is to get our time for the first byte of transfer to happen to be as low as we can. That's network latency part. And it's a very hard problem to solve. Network bandwidth is somewhat easier because you can add more network adapters or you can use fatter pipes and so on. So it's engineering in some sense. Network latency, it's physics, right? There's only so much you can push to get the network latency down. Now, that doesn't mean that we cannot play some tricks. We can go and shave off some of the software overheads. We can have a better integration between the network and GPU systems to have lower latency communication and so on. And of course, we can do algorithmic optimizations to try to improve the network latency, getting it as close as possible to this theoretical limit that is imposed by physics, as close to that as possible. So in this picture, we talk about one such algorithm, which is called direct data access, where each GPU, instead of using a send and receive sort of communication model, it uses a direct access model to the other GPUs. It's very similar to RDMA communication on networks, but it's more in the context of load store accesses over NVLink, which are also like load store put get sort of communication. This allows us to compress all of our communication kernels into a single fused kernel and minimize the latency software overheads associated with that to the bare bones, how much ever we need. Okay. All right, with that, let me hand it off to Adi to tell us about the next steps or where Meta is heading to for our next generation systems.
Thanks, Pavan. So, summarizing, GenAI workloads, both from a model training perspective as well as model serving perspective or inference perspective, are generally sensitive to the kind of networks we design, as well as the software or communications libraries that abstract these networks away from our workloads. Now, as we trained Llama 3 and as we served it in production, we ran into a number of problems related to performance optimizations. And those problems were highlighted by small message performance or small collective performance, load balancing issues, or overall network latency sensitivity of the workload itself, right? We solved these problems by tuning the communications library as well as coming up with new collective algorithms as well as new load balancing algorithms in order to better load balance all of this traffic. So that's all the work that we did. But what's next? We're not done pushing the boundaries of scale, not yet. In the near future, we'll be scaling much larger models. And these will require an order of magnitude more GPUs. That has two consequences to all the work we are doing. So the first consequence is that it's not possible to fit all of these GPUs in the same physical region or same building. So that means that some of the GPUs will be farther apart than others. That pushes us to investigate or look into if the same lossless protocols that have been, and transports that have been helping us move the bytes around for these training clusters, will it be still applicable and useful and performant when the network latency becomes much higher? Or we need to investigate into lossy protocols, right, or lossy transports. The second consequence is as these models grow larger and larger in size, especially the dense parts of the models that require a lot of communication, we also need to invest in increasing the scale-up domain size from 8 GPUs today and staying within the server to going across the server and to potentially hundreds of GPUs. As we do that, we have a trade-off or a choice to make. if we actually make the choice of building these scale-up networks as shared memory on top of shared memory models, then that comes with a much higher reliability bar as compared to our scale-out networks that we talked about today, right? Now, we need to come together in terms of how we address those reliability challenges as well as how we design those protocols. I mean, that's about what's coming next in training. But in terms of serving, I cannot underscore the importance of model serving more. As these bigger and bigger models get trained, getting them to the users is where serving is a very critical part of this overall journey of generative AI. And that means that, for things that Pavan mentioned, like small messages or small to medium messages, that he's not put that much focus on in terms of like how we optimize for latency, that becomes like really critical part of our future work. So these are really, really hard problems, reminding us that we are only at the beginning of our journey. Overall, it's a very, very exciting time to be working on networking and communications, which is a very, very critical part of scaling generative AI models to be large as well as performant. Many of you in this room are here because you care about similar problems that we do and are solving similar problems. So if you have some comments or feedback about how you are solving these problems or curious about why we are solving a particular problem in a particular way, please reach out to us. We'd be very, very happy to chat with you after this talk. Thank you so much for your time.